All right, section 12.3 today, people. Last section of the chapter and the book. So, congrats on getting it all the way. We're gonna be looking at inference for slope today. So 12.1 and 2 was about chi-squared. 12.3 is actually kind of an extension of chapter 3. So it should be a little bit of a review for us, at least at the beginning. Learning targets. Check the conditions for performing inferences about the slope beta of a population true regression line. Interpret the values of A, B, S, and standard error of B in context, and determine these values from computer output. Construct and interpret a confidence interval for the slope beta of the population regression line. Perform a significance test about the slope beta of the population true regression line. So here is an example of it's a scatter plot of the duration and interval between an eruption of Old Faithful for all 263 eruptions in a single month. So basically, on the x-axis is how long Old Faithful was going for, and then the y-axis is how long it took until the next one happened. And then we were able to draw in this blue line is the population least squares regression line. Now, this is the population least squares regression line for that month, right? It was every single data point for that month. So that's why it's the population least squares regression line. So just some information. A regression line calculated from every value in the population is called a population regression line. The equation of a population regression line is mu y equals alpha plus beta x, where mu y is the mean y value for a given x value. Alpha is the population y-intercept, and beta is a population slope. What we talked a lot about was actually a sample regression line, which is calculated from a sample, right? And it's the estimated regression line. And that's why it's y hat equals a plus bx. And why we were so particular in chapter 3 to use y hat was for this reason. It was a sample, so we had to have the notation be sample. So y hat is the estimated mean y value for a given x value. A is the sample y-intercept. B is the sample slope. So here is one sample. Again, we have that blue line in context for us, but green is the least squares regression line based on this sample of 15 data points. And we have two more. So each one of these is an individual sample of 15 data points. And then from there, you drew in the least squares regression line for those 3 points, or for those 15 points. And then the blue line is just there as a reference. All right. And so you can see how much the line changes, and specifically the slope changes based on those 15 points. And that's kind of that's a reminder of what sampling variability is, and it's where each sample will kind of be a little bit different. We expect it to be pretty close to the population, but each sample is slightly different. And so each one of these 15 samples we see are slope 10, 12.5, 15.7. So they do change quite a bit. And that's exactly what we're talking about here. And that's all compared to the population line, which was 13.29. Yeah. And so thinking back to, I believe, chapter 7, which was sampling distribution. We're not doing a sampling distribution of B, but before sampling distribution is every possible sample. So if we took that data from Yellowstone's Old Faithful, and we found every possible sample of 15, and we found the least squares regression line of that sample, and plotted that value for B on a dot plot, we would get this distribution here. It would be every single possible sample. All right. Some things about the sampling distribution is that the mean of the sampling distribution is this blue line. And it actually also, it equals the population slope. or the population B, right? So the nice thing about the sampling distribution is that it's centered at the population. Some other things to notice is, hey, it's normal, and we talked about that, especially as regardless of the shape of the population, as your thing gets larger, this becomes even more and more approximate. Now, 15 is a little bit small, but that's okay. We still see that this is approximately normal. The center, like we said, mu b is going to equal beta. And since they are equal, they are an unbiased estimator of each other. The variability of B, so that comes from, if you looked at sampling distribution, standard deviation, you would see a very similar formula here, but it's the sigma divided by sigma of x divided by times square root of n. Right? So our variability here is 1.42. And so this is just that basically that same slide, but in a generic form. So choose an SRS of n observations of x comma y from a population of size capital N with the least squares regression line mu y equals alpha plus beta x, and B is the slope of the sample regression line. Then the mean of the sampling distribution of B is equal to beta. The standard deviation of the sampling distribution of B is approximately sigma of B is approximately sigma divided by sigma of x times square root of n, and the sampling distribution is approximately normal. So when the conditions for inference are met, the regression model looks like the one shown here. The line, that red line right here, is the population regression line, which shows how the mean response of mu y changes as the exploratory variable x changes. So as our x increases or decreases, our mean might change as well, right? If the mean gets bigger, that means that this is a positive correlation. If it was getting smaller, as x got bigger, then it would be a negative correlation. But basically, at each individual point on this line, we would have its own normal distribution. Right? So this is an example of just 3 normal distributions based on those x values, but there are many, many more. So there are 5 conditions in order to check this and proceed for inference. Now, some of them are very similar, but suppose we have n observations of a quantitative variable x and a quantitative response variable y. Our goal is to study and predict the behavior of y for a given value of x. So right off the bat, linear, the actual relationship between x and y is linear. For any particular value of x, the mean response mu of y falls on the population regression line. And right, this makes sense for it to be linear. Why would we use the linear regression if it's not linear, or do a test for linear regression if it's not linear? So that's got to be linear first. Independent, individual observations are independent from each other. When sampling without replacement, check the 10% condition. So that's what we've been checking a lot before. Normal, for any particular value of x, the response y varies according to a normal distribution. We'll look at that, very similar to what we did in chapter 11, actually, as well. A slightly new one is equal standard deviation. The standard deviation of y is the same for all values of x. So the variability doesn't change depending on your x, which is important. And then random, the data comes from a random sample from the population of interest or a random experiment. This is just a slide to kind of highlight how you remember LINER. But yeah, we'll just keep going. It's not super important. They're very similar. The 2 new things are equal standard deviation and it's linear. And right off the bat, if it's not linear, you shouldn't even do a regular linear regression. So it wouldn't make sense to do an inference for it either. So the new thing to remember is equal standard deviation. So Again, this is a nice review from chapter 3 of how to examine linearity. So you can look at the scatter plot and see if it kind of follows a linear pattern. And then also take that and go to residuals. And the main way to see is if the residuals have a pattern, then the data is not linear. So we see here, these are not similar graphs. This is a residual plot, and we see this U-shaped pattern, so it is not linear. So as long as there's no curved patterns in the residual plot, we're good to go. This one has one, so it would cause concern. For independent, this is a very clunky definition, but knowing the value of the response variable for one individual shouldn't help predict the value of the response variable for another individual. If sampling done without replacement, remember to check the sample is less than 10% of the population size. So to make sure that the population is large enough for these data points to be considered independent. Normal, make a histogram, dot plot, sum plot, box plot, or normal probability plot of the residuals and check for strong skewness or outliers. Ideally, we would check for the normality of the residuals at each possible value of x because we rarely have enough observations at each x value. We make one graph of all the residuals and check the normality. This one is the biggest new one, equal standard deviations. So you want to look at the scatter of the residuals above and below the residual line equals 0. The variability of the residuals in the vertical direction should be roughly the same from the smallest to the largest x value. So you can notice, regardless of where you are as an x value, the residuals are about the same. These two vary about as much as these two. This point that varies as much about some of the other points. So regardless of where they are, they're kind of varying all over the place. Versus on the right-hand side, you can see that as the data gets larger in X, the variability gets a lot larger. And you kind of have a cone pattern here, which is not good. Random, see if the data come from a random sample from the population of interest or a randomized experiment. If not, we can't make inferences about a larger population or about cause and effect. That should be a review for all of us. So here's a problem. Ms. Bartley's class did a fun experiment using paper helicopters. After making 70 helicopters using the same template, students randomly assigned 14 helicopters to drop each of 5 different heights. Teams of students released the 70 helicopters in a random order and measured the flight times in seconds. The class used computer software to carry out a least squares regression analysis for these data. Here are a scatter plot, residual plot, and histogram of the residuals. So check whether conditions for performing inference about the regression model are met. And yeah. So first things first, linear. Well, you could see there's not really a pattern in the residuals. I know you're like, well, what about all these vertical lines? That makes sense because there's a lot of data points at the same x value. But there doesn't seem, it's not like all of the 200s are lower and lower, and then it starts getting bigger and makes a U-shape that way. They're all kind of spread out about that line, y equals 0. So linear is good. Independent, it says because the helicopters were released in a random order and no helicopter was used twice, knowing the result of one observation should not help us predict the value of another observation. And that's important because what happens if you dropped all of them at the same time, or roughly at the same time from the same height, and the wind was blowing or the air was blowing at that time? Well, then all those data points might be slightly skewed. But since they were dropped at random times from random heights, we are good with this independent condition. The next two are the normal and equal standard deviation. So normal, there is no strong skewness or outliers in the histogram. You can see that right here. So it's good to see. Equal standard deviation, and notice it is about the residuals, just so you know. We are dropping the residuals here to check for normality. For the equal standard deviation, the residual plot shows a similar amount of scatter about the residuals y equals 0 from each drop height. But flight times seem to vary a little more for the helicopters that were dropped from a height of 307, which is kind of true, but I think overall it's not too bad. And don't stress out too much about these conditions. If it's pretty close, just continue on and state that it is. Don't say like, oh, it's about this or it's close to this. If it's close, just make your decision and go with it. Random. The helicopters were randomly assigned to the 5 possible drop heights. So good there. So all 5 points are checked. Linear, independent, normal, equal standard deviations, and then random. And that's kind of what I just said. Don't freak out about minor issues when checking the conditions. And honestly, usually the test will say the conditions for inference have been met, proceed. So they don't always make you check all 5 conditions. It's good to know what 5 you have to check, but a lot of times they are given to you. So estimating the parameters. When the conditions are met, we can do inference about the regression model mu y equals alpha plus beta x. The first step is to estimate the unknown parameters. So if we calculate the sample regression line, y hat equals a plus bx, the residuals estimate how much y varies about the population regression line. So A estimates alpha, B estimates beta, S estimates sigma. So when conditions are met, the sampling distribution of the slope B is approximately normal, with the mean of B equaling beta and the standard deviation being this formula here. We estimate the variability of the sampling distribution of B with the standard error of the slope. So standard error is S over Sx, S of x times n minus 1. That n minus 1 is used since we're using a sampling distribution. It's needed in order to keep this kind of accurate. The reason for it is not needed to know in this class. Just know that the standard error here is n minus 1 instead of 2. And you interpret the standard error as how far the sample slope typically varies from the population slope if we repeated the data provided processed many times. So just how far we vary, which should make sense. So here's a bunch of data. It wants us to find the estimate for alpha. Well, this is a good reminder of our Minitab outlet. Remember, coefficients is really what we're looking at. Those are our A and our B values. The constant, if we think about our sample linear regression, it's y hat equals A plus bx. So A is the constant. So the constant and the coefficient, this is my A value, this is my B value. So the estimator for alpha is going to be A. Okay, I don't know why, oh, this didn't save. This should be, hold on. Sorry, I made these corrections, but they didn't save. So A equals negative 0.03761. And the way to interpret it is if a helicopter is dropped from 0 centimeters, it will take that amount of time, the amount of seconds to land on average, right? Because A is our y-intercept. So that's just kind of how you interpret it. And you can kind of decide, well, in your own head, if you think this makes sense to interpret A or not. I would say it wouldn't make sense to drop helicopter from 0 centimeters, because it technically should just be at 0. Now negative 0.037, fairly close to 0, but it should be 0. Our B value now, so this is our constant. Our drop height is our variable, our x variable, so that's going to give us our slope. And B is going to estimate beta. So B is equal to this. For each increase in 1 centimeter in drop height, the average flight time increases by blank seconds. So when you're interpreting this value, that's really interpreting slope. A is interpreting the y-intercept. B is interpreting the slope. We use S to estimate sigma. So our S here is actually, it's given to us here, boom. And it's the actual flight time typically vary about blank seconds from the time predicted with the least squares regression line using x equals drop height. So it's about how far it typically varies. And then given the standard error, the slope has to be interpret this value. So we are given SE coefficient, and it is of the slope. So it is kind of nice that it's right back down here for our B value. I guess you could, yeah. So, and it says, if we repeat the random assignment many times, the slope of the sampling regression line would typically vary by that from the slope of the true regression line for predicting flight time from dropped heights. So the question is, what's the difference between B, C, and D? C is just the actual time, flight times. It typically varies by about the regression line. And for the standard error of B, that's really the slope. It's how much the slope varies. So just a little distinction between the two. All right. Almost done with, I think it's the second to last subsection. So it's constructing a confidence interval for slope. So remember, our confidence interval is always statistic plus or minus critical value times standard deviation of statistic. So here, if we're doing the confidence interval for slope, our statistic is going to be our slope, but we use our beta as our population, so our statistic is B. So we're going to use B plus or minus critical value, which is going to be T star, times SE of B, right? It's the standard deviation of the statistic. So since I'm using B, it's going to be SE of B. And we have two variables here. So our degrees of freedom is going to be n minus 2 in this case, just as a forewarning. So good caution. The values of T given in the computer regression output are not the critical values for a confidence interval. You just need to find them, and by doing your inverse T and then putting in the probability and the degrees of freedom is how you can find that on your calculator. So here's an example. If I have the data, I think our calculator could do this. I have pulled up. So stat edit. This will give you a chance to also put this data in. So hopefully you have the data in. If not, pause it and make sure to put it all in, and then we'll get started. So everyone knows that cars and trucks lose value the more they are driven. Can we predict the price of a used F Ford 150 if we know how many miles it has on the odometer? A random sample of 16 used F-150 Super Crew 4x4s were selected from among those listed for sale on Autotrader.com. The number of miles driven and price in dollars were then given. So construct and interpret a 90% confidence interval for the slope of the population regression line. So here is our Minitab output for it. We have our residual plot histogram, which is approximately normal, so I think we're good there. We'll get into it all. We'll use those to check our conditions, but we're going to do the four-step process like we have. So we're stating, remember this is a confidence interval, so it's been a little while since we've done it. So in our confidence interval, we want to state the confidence level we're doing and the parameter we're looking for. So we're doing a 90% confidence interval for beta, the slope of the population regression line relating y equals price to x equals miles driven for used Ford F-150 Super Crew 4x4s listed for sale on Autotrader.com. In the plan phase, we just state the name, which is the t interval for slope, and then check the conditions. So for linear, the scatter plot shows a clear linear pattern, and also the residual plot showed no leftover curve pattern. So go back. Residual, no curve pattern, so we're good there. We'll skip independent for right now. The normal statement, like I said, this is approximately normal. So the residual histogram plot is approximately normal, so we're good there. I believe it says a random sample of 16, so that's the random right there. The equal standard deviations, the scatter plot points around the residuals of equal, the residual line equals 0 appears to be about the same for all x values, right? For this residual, it's not, regardless if you're really far to the right or really close to the left, the residuals are about the same. There's no clear pattern there. And then independence, the last one, we assume that 16 is less than 10% of all used Ford F-150 Super Crew 4x4s. So conditions are met, so we're going to proceed into the do phase. The do, you need to state your degrees of freedom. So 16 minus 2, because it's two variables. Find our t star. We're doing a 90% confidence interval, so you can do calc. Second distribution. Inverse, no. Oh, I don't have inverse t on here, so I'd have to use the table. But you can use your inverse t knowing your degrees of freedom and that it's 90% confidence interval. Then it's b plus or minus that t star times SEB. I think all that information was given on the Minitab output, and that's how we got our confidence interval. To conclude, we are 90% confident that the interval from blank to blank captures the slope of the population regression line relating y equals price to x equals miles driven for used Ford F-150s. Super Crew 4x4 is listed for sale on Autotrader.com. So just remember, right, we are blank percent confident that the interval from blank to blank captures the true blank. That's our template always for confidence. All right, let's see if my calculator has this on here to do it for us. So I believe on the new, well, let's see. I believe on the new calculators, you probably have the linear regression interval. I only have the test here, but it should be very similar. what you can see if you had the new calculator and you plug this in, you should get the same. Right here would be our interval. Again, my b-val, my degrees of freedom, my s, my a, my r squared, and r. So on here, you don't get your t star, so you need to know how to do that by hand, and it doesn't give you your standard error for b also. But I think those were given to you in the problem in the Minitab output. All right. So when you see a list of data values on an exam question, wait a moment before typing the data into your calculator. Read the question through first. Often the information is provided that makes it unnecessary for you to enter the data at all. This can save you valuable time on the AP Stats exam. So I'm glad that we wasted your time right now in the video and not on the AP exam to note that, hey, I didn't really need to do all this on the calculator, because if you go backwards, everything that was needed, I believe, I started off with it. Boom, right there, had a Minitab output, so I didn't really need to do this. But it's okay. Like I said, I'm glad I wasted your time now than on the AP test. So, last subsection is performing significance testing for slope. So remember, significance testing, our standardized test statistic, usually that's our z score or our t-score, is statistic minus parameter divided by standard deviation of that statistic. So here it's going to turn into b minus hypothesized slope divided by SE sub b. Right? And I believe this is, again, we're not going to type all that data in, but we could, and I'll do the test for the data I have in my calculator right now. I'm not going to do it for here. But for this problem, infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Child development researchers explore the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of the foot caused the infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the child's IQ at age 3 and using the Stanford Binet IQ test. The table contains data from a random sample of 38 infants. So here's all the data that I need, and it asks, does this provide evidence, give convincing evidence at the alpha of 0.05 for a positive linear relationship? So if it's a positive linear relationship, that means that my b is going to be greater than 0. So when I go in to do my test for significance, right, it's going to be the 4-step process. First one, state, hey, my slope is 0, and then my alternative is, hey, my slope or my beta is actually greater than 0. And that's beta, where beta equals the slope of the regression line relating y equals IQ scores to x equals count of crying peaks in a population of infants. And we're going to use alpha equals 0.05. So those are the 3 things you need in your state phase: null hypothesis, alternative hypothesis, and alpha level. In the plan, we're doing a t-test for the slope, and then we got to check our 5 conditions. Linear, boom. The residual seems pretty random, so we're good there. Independent, 38 is less than 10% of all infants, so this is certainly independent. For normal, the residual histograms looks approximately normal, or really doesn't show any strong skewness or outliers. It's probably what I should have said earlier too. It doesn't have to look normal. It will probably be normal, if not just symmetric, but the main thing you're looking for is that it doesn't show strong skewness or outliers. Equal standard deviations, that means that the typical amount it varies, well, each point varies is its own residual. So as long as all these residuals are about the same or randomly placed, then we're in good shape. And here they are. There's not a specific point that's like really far in the x and also really has a really large residual. They're all pretty scattered evenly. And then random sample of 38 infants. So plan's done, now into the do phase. So do, find our t value, our p-val, boom, boom. And here, this is a good note, because our p-val is for a two-tailed test, right? Whatever here is because when you do a hypothesis testing, it's always a two-tailed hypothesis. Or sorry, a confidence interval is always two-tailed. So this p-val is going to actually be two-tailed also. The default is two-tailed. So when to find the actual p-value, you want to take that p-val divided by 2 and go from there to get to be one-sided. And then conclusion, because the p-val of 0.002 is less than alpha, which is 0.05, we reject H0. There is convincing evidence of a positive linear relationship between the count of crying peaks and IQ scores in the population of infants. All right, let me show you this on the calculator really quick. And my buttons are going to be wrong because I'm doing the data from the previous one. The linear regression test, if you didn't see how I got there. Stat, test, linear regression test. Boom. Then you just press calculate, and then this would be my t-test from the problem before. And obviously it's going to be different because my data is substantially different. But this is what you'd get out of your calculator. What you probably want to look for is that t-val and your p-val. So our p is very, very large here in this problem. But here, get our degrees of freedom. On your table, you can see A, B, S, R squared, and R as well. Probably the most important of those A, B, and S. And that is it. Our last learning targets of the year. Here you go. Thanks for watching.